Have you ever wondered how a tiny problem can just suddenly blow up into a massive one? Or maybe how an investment grows kind of slowly at first and then all at once? Well, the secret behind that isn't magic. It's math. And today, we're going to decode the powerful equations that control that kind of explosive growth and reveal the hidden patterns that are shaping our world.
Believe it or not, our story starts with just one number, 24. See, back in 1859, a landowner in Australia decided to release just 24 European rabbits into the wild, for a little bit of sport hunting.
Seems harmless enough, right? 24 rabbits? Well, with tons of food and almost no natural predators, this happened. In just a single decade, those 24 rabbits exploded into a population of millions. That, right there, is the dramatic, almost unbelievable power of exponential growth in action.
So this brings up a huge question. How on earth do you even begin to model growth that's that explosive? I mean, what kind of mathematical tool can possibly predict something so incredibly powerful?
Well, the answer lies in what we're going to call the exploding rabbit problem. And this story is our gateway to understanding the main tool for this job, the exponential equation.
So, what exactly are we dealing with? An exponential equation. And here's the thing that makes it so different from the algebra you're probably used to. The variable, the x we're trying to solve for, isn't down on the main floor. It's living upstairs, in the exponent. That little detail, that unique structure, is the secret sauce that lets us model these intense patterns of growth and decay.
All right, so to tackle these kinds of equations, you're going to need a toolbox. Let's start by grabbing your first and most direct tool, a really clever method that's all about matching bases. Now, this tool works because of a beautifully simple rule. It's called the one-to-one property. All it really says is that if you have two identical bases on either side of an equal sign, well, then it just makes sense that their exponents have to be equal too. It's a surprisingly elegant little shortcut.
So how do you actually use it? It's pretty straightforward. First, you try to find a common language or a common base for both sides of the equation, like, for example, the numbers 8 and 16. They can both be written in terms of the number 2. Once you get those bases to match, that one-to-one property lets you completely ignore the bases and just set the exponents equal. And boom, all of a sudden a really complex-looking exponential problem turns into simple algebra.
But, matching bases is kind of like using a hand screwdriver. It's great for certain jobs, but for the really tough stuff, you need a power tool. And in the world of exponents, that power tool is the logarithm. Because what happens when the numbers just don't cooperate? I mean, what if you have a 5 on one side and a 4 on the other? There's no simple whole number base that they share. Our first tool is totally useless here. We're stuck.
Or are we? This is where logarithms come in to save the day. And look, don't let that word intimidate you. A logarithm is just a tool that was designed for one very specific job, to get a variable out of an exponent. It's the inverse, the perfect opposite of raising something to a power. And the process is incredibly powerful. First, we just take the logarithm of both sides. Then comes the real magic trick. There's a special power rule that literally lets you grab that exponent and bring it down to the main level. And just like that, the variable's freed, and it becomes a simple algebra problem that you already know how to solve. Okay, so we figured out how to get variables out of exponents. But what if the equation starts with a logarithm? Let's flip the script for a minute and see how to solve these kinds of logarithmic puzzles. The main strategy here is just to undo the logarithm. Your first move is to get the log expression all by itself on one side of the equal sign. Then, you use that fundamental relationship between logs and exponents to rewrite or convert the whole equation into its exponential form. This simple switch transforms the problem back into a format that's way easier to handle.
Now, this next part is really important. Sometimes when you're solving a logarithmic equation, the algebra will spit out two potential answers. So, in this example, let's say we find that x could be 3 or x could be -1.
So it looks like we're done, right? We can just pack up and go home? Well, not so fast. The most critical question you have to ask yourself with every single logarithmic equation is this: are both of these answers actually valid?
Because here's the single most important rule you need to remember. Logarithms have a really strict bouncer at the door. The value you're trying to put inside the function, what we call the argument, it must be positive. It can't be 0, and it definitely can't be negative. There are no exceptions.
And that rule is exactly why you have one last mandatory step. You must always plug your answers back into the original equation to check for what are called extraneous solutions. These are answers that look totally correct algebraically, but they break that fundamental rule of logarithms when you actually check them.
Okay, let's build a quick little cheat sheet for all this. When you see an equation, the first thing you ask is, can I match the bases? If the answer is yes, just use that simple one-to-one property. If the bases are different, it's time to break out the power tool, logarithms. And if the problem starts with a logarithm, your goal is to flip it back into its exponential form. That's your core strategy right there.
So we've built this whole mathematical toolbox. But these tools aren't just for solving problems in a textbook. Now, let's see where they actually show up at work, shaping the world all around us.
Yeah, this isn't just abstract math. We are talking about the exact formulas that model population growth, just like with those rabbits. They calculate compound interest in your savings account, they're used for carbon dating ancient artifacts, figuring out drug concentrations in medicine, and even processing signals in engineering. Seriously, these equations are everywhere.
And this is the true power we've been talking about all along. Whether it's in high finance or fundamental physics, these simple equations give us a lens to predict what's coming next and to make sense of everything that's already happened.
So, I'll leave you with this final thought. Now that you have the tools to actually see them, what unseen exponential patterns in technology, in nature, maybe even in your own life, are shaping your world right now?